Good afternoon. My name is Andre Leclerc, and I am an engineer at Marshall Space Flight Center, where I do user support and training for GFSSP, along with Alok Majumdar, who is the chief developer of GFSSP. Today, I'll just cover some brief background about GFSSP. We'll look quickly at the equations that it solves internally. We'll see the resistance options that come built into the code, as well as the fluid options in our library. And then we'll take some time to build a few models and then look at some pre-built models as well to see the capabilities of the code. GFSSP stands for the Generalized Fluid System Simulation Program. It's a general purpose computer program for computing pressures, temperatures, and flow distribution in a flow network. It is a finite volume 1D network flow solver. It was originally developed to support the fast track engine program, primarily to look at secondary flows inside the fast track turbopump, as well as to model some of the propulsion systems that were used in testing of fast track on the ground. GFSSP development started in 1994 with the goal of providing a very generalized flow analysis tool, as opposed to earlier turbopump codes that had been specifically written for specific engines. In 2001, it was selected for the NASA Software of the Year award. If you are a NASA civil servant or a NASA on-site contractor, that is, you have @nasa.gov as your email address, GFSSP is free for you to use. You can simply contact me and I can get you a copy of the code. GFSSP is also free for civil servants of other agencies and for any contractors who have any federal contract. Doesn't have to be just a NASA contract. But that has to be requested at software.nasa.gov. We also have an educational version available at software.nasa.gov. It lacks Fortran user subroutine capability, but otherwise contains all the built-in features of the code. And many universities have used it when teaching senior level thermal design classes in mechanical engineering. We have more information available at our website, nasa.gov/GFSSP, including our user manual, our class notes, and several papers that have been written over the years with different GFSSP models. When we think of computational fluid dynamics, we usually think of Navier-Stokes analysis, where you have millions of nodes and you're solving the full Navier-Stokes equations. But CFD can also include what is known as network flow analysis, or nodal codes. In this case, your momentum equation, instead of a full Navier-Stokes equation, is simplified into empirical relations. So GFSSP is an example of a finite volume network flow analysis code. Other network flow analyzers include Syndifluent, EZ5, and GT Suite. Typically, you'll do a full Navier-Stokes CFD analysis when you're looking at a single component and you need detailed flow results of that single component. And this will be because of the long time needed to run these models. It's often used after preliminary design. Whereas a network flow analysis tool such as GFSSP is often used during preliminary design, and it usually looks at more of a system level, including several components. And the transport processes are simplified by using empirical laws. For example, pressure drop in a pipe is FL/D times 1/2 rho V squared. This is an example of a typical GFSSP network. Over on the left, we see a boundary node, that's the double box. In that node, you set the pressure and temperature at the boundary. And that becomes a boundary condition for your differential equations that you're solving. Inside the model are internal nodes or fluid nodes. In these nodes, we solve conservation of mass and energy in order to get pressures and enthalpies and therefore temperatures. Between these nodes, we have branches. In the branches, we solve the momentum equation to get flow rates as functions of pressure drop between the nodes. Now you can connect a solid wall to your fluid model with conjugate heat transfer, and these dark nodes are the solid nodes. In those, you solve the energy equation to get wall temperatures. You can connect solid nodes together with solid-to-solid conductors, which model conduction, or you can connect them to your fluid node and model convection. When working in GFSSP, our graphical user interface allows you to work with various units in both English and SI, although internally the code is written in English units. So when writing user subroutines in Fortran, it's important to remember to work in terms of feet, pounds, BTUs, degrees Rankine. But again, outside the code, you have your choice of units. Our sign convention is the same as you find in undergraduate thermo. Mass into the node is positive, mass out is negative, heat into a node is positive, and heat out is negative. There are 6 types of unknown variables that are possible in a GFSSP model. Those are pressures, flow rates, temperatures of fluid nodes and solid nodes. If there are multiple fluids, there are these concentrations of the species, and then the mass inside any node volume. And to solve these, you can do simultaneous solution of your mass and momentum equation, your energy conservation equations for both the fluid and solid, separate conservation equations for the different species if you have multiple species in your model, and your equation of state gives you the density as functions of pressure and enthalpy, or pressure and temperature, and that times the volume gives you the mass in the node. Mass conservation simultaneously with the momentum equation. And the momentum equation does contain pressure and flow rate. The basic form of our momentum equation contains a pressure drop term and a friction loss term, where the friction loss is functional to the flow rate squared. But you have the option of activating extra terms in the momentum equation depending on the type of analysis you're doing. You might use the unsteady term if you're doing a water hammer or priming analysis. If you have a high speed but still subsonic compressible flow, you can activate the inertia term. If you're sending a fluid uphill, you can turn on gravity. If you're modeling a turbo pump, you might want to activate the centrifugal term when you have fluid moving outward from your axis of rotation. Our energy conservation equation can be written either in terms of enthalpy or entropy. We usually use enthalpy. And it's based on an upwind scheme. That is, the enthalpy of a node is based on the enthalpies flowing into it and the enthalpy going out of it. So the rate of increase of internal energy in a node in a time step delta tau is going to equal the rate that enthalpy flows in, m dot h, from the upstream nodes, the rate enthalpy flows out, m dot h, leaving the node, and then any heat source Q, where the user can either define that heat source in BTUs per second or in kilowatts, or the code can calculate a heat source coming from the solid wall if you have conjugate heat transfer in solid nodes. Our solid conservation equation is just the change in energy of a solid node, the MCPT of a solid node, is equal to the net sum of heat conducted into the node. So that's Ka delta T divided by some distance delta, and any heat being convected either to the fluid or to a defined ambient node. So that's an HA delta T. And that equation can then be rearranged putting the temperature of the node on one side so that you get a successive substitution form. When working with the code, you're normally going to use mostly our graphical user interface, which is called MIG, Modeling Interface for GFSSP. In MIG, you create your flow circuit by pointing and clicking on a blank canvas. You enter in your input values, you start GFSSP running, and MIG generates the text input file. Then, after GFSSP is done running, you can look at your results in MIG. You can plot them in MIG's plotter or in the separate win plot. GFSSP itself is basically just an equation generator and solver that happens to be linked to fluid property programs. Now, GFSSP also contains calls to empty user subroutines. And in those subroutines, you can write your own customized Fortran, which can then be compiled and included in the code for your own custom executable. So you can add, if you have your own type of flow resistance that's not included in the GFSSP library, you can program the equations of pressure drop with respect to flow rate inside a user subroutine. We have a small library of resistance options that are built into the code. These include pipes, restrictions, non-circular ducts, thin and thick incompressible orifices, reductions and expansions. If you're doing turbopump modeling, you might use the rotating annular duct or the rotating radial duct or the Labian face seals. We have common fittings and valves such as elbows, 180-degree turns, gate valves, butterfly valves. So you select that and it puts in a standard K value for that fitting. You can model a pump if you have a manufacturer's pump curve, or you can simply model a pump as a power and an efficiency. If you have a valve and the manufacturer has given you a CV, you can enter valve characteristics as CV. You can model viscojets, which are a type of a device that creates a very high pressure drop so that you get two-phase flow coming out of the viscojet. You can do a control valve where GFSSP monitors the pressure in a node, and if the pressure gets too high, it closes the valve. If the pressure gets too low, it reopens the valve to let flow in.
Andre, we've got
Yes.
one question for you. They'd like to know if VTASC is being deprecated in the code.
Yes, VTask is our old graphical user interface that we had for many years. And yes, we recommend that it no longer be used. MIG has taken over. And in fact, our latest version, which we will soon be releasing, there is no VTask for it anymore. It's all entirely in MIG, yes. You can model the pressure drop in a heat exchanger core or in a series of parallel tubes. You can look at the choked flow in a compressible orifice if you're flowing a gas over a large pressure drop. You can set a fixed flow rate, which is basically a type of pump with a vertical pump curve. And we do have what we call a Cartesian grid. That would allow you to do a very simplified 2D model, but at this time there's no turbulence modeling in it, so it's really just for simple laminar flow problems. It's really more of academic interest right now. And there's a user-defined branch as well, where you can model the pressure drop versus flow rate of code and program the equations for it yourself in Fortran. Our fluid options, most of the time we use the GASP-WASP library. GASP and WASP were developed at NASA Glenn back in the 1970s. These codes are very fast and very forgiving, and they contain the fluids most commonly used in propulsion, like helium, methane, nitrogen, oxygen, and parahydrogen, as well as water. Water is often used in testing anyway. We have RP1 interpolation tables. You can model an ideal gas where you give the R value. You can make user-defined tables, interpolation tables of your properties. If these tables are coming from RefProp data, we actually have a utility that comes with the installation to help you convert RefProp output into GFSSP user-defined tables. And we also have the GasPack fluid library, and this is a commercial code that was sort of an ancestor to RefProp. In addition to the fluids that GasP has, it also includes hydrocarbons and refrigerants and liquid peroxide. So at this point, I'd like to start building some models to give you an idea how the code works. So what I'll be building today is a simple model of the blowdown of a pressurized tank. So assume we have a tank that is 10 cubic feet. It's initially at 100 psi and 80 degrees Fahrenheit. And someone opens a valve, so air starts leaving to the atmosphere at 14.7 psi through an orifice with diameter of 0.1 inches. And we want to know how the pressure and temperature inside the tank will change with time. So I'll go ahead and leave PowerPoint and start up MIG. I will create a new model. And I will call this Demo 1 Tank Blowdown. It asks me to choose a working folder. And then in that working folder, I will specify that the name of my model file will be demo1.gfsssp. This opens up the model properties window. And what we do next is these 6 tabs will work from left to right, filling them out. So you can see our input file and output file have been named automatically demo1.dat, demo1.out. But we can always rename them if we want to do multiple runs of the same model, but with slightly different inputs. We'll use the default executable, which is GFSSP702.exe. And I'm going to use English units here, but if I wanted my output in SI units, I could select that as well. I'll move to the next tab over. This is the steady unsteady tab. This is a transient analysis model. We want to see pressure and temperature changing over time, so I'll choose unsteady with a time step of 0.1 seconds and a final time of 300 seconds. The circuit tab is where we activate those extra terms in the momentum equation, as well as turn on certain options. We're not going to use this tab just yet. At the fluids tab, we select our fluid. The easiest way to model air is just to assume it's an ideal gas. So I'll select ideal gas, and by default, it fills in the constant and C sub P viscosity and conductivity for air at room temperature. Our solver tab gives us control over the solver, such as the convergence criteria, the number of iterations, any under relaxation we want to apply. For this simple model, we'll just leave everything set to the default. And on the output tab, because I selected an unsteady model, it's automatically selected to create a wind plot file, which will enable us to plot our results over time. Our default is a binary file that only WinPlot can open, but you could also do a CSV file in case you wanted to do plots in another package like Excel. I'll hit OK. And now we're ready to build on the canvas. So I'll select the internal node and drop it on the canvas. This will represent the mass, the volume of our tank. And then I'll select the boundary node, the double box, put that on the canvas. And this will represent the ambient boundary at 14.7 psi. And then I will connect the two with a branch. So now I will go to node 1, right-click, go to Properties, and I'll go ahead and describe this as the tank. The initial condition will be 100 psi for pressure, 80 degrees Fahrenheit for temperature, and the node volume is the volume of our tank, so I will switch that from inches cubed to feet cubed, and put in 10 cubic feet for our node volume, and hit OK. Over at our boundary node, I'll go to Properties. Now, in an unsteady model, your boundary conditions might be changing with time, so it asks you to create a history file. So I will click Edit for the history file. At time 0, our boundary is 14.7 psi, 80 degrees Fahrenheit, and the mass fraction of our error is just 1. And at time 300, the pressure is still 14.7, temperature still 80 Fahrenheit. So this is a very boring history file. What GFSSP will do is in every time step, it will interpolate the boundary pressure and temperature from this file. Now I will add our branch. So for this branch, we have an orifice, but I'm not going to use the restriction. Instead, I'm going to use the compressible orifice option. And this option checks for choking. If you have a gas flowing through an orifice and you know the upstream pressure is going to be more than about twice the downstream pressure, the gas is probably going to choke. In this case, we have 100 psi going to 14.7, so that's a lot more than 2, so it'll definitely choke. I'll right-click the branch and go to Properties. It asks for the area. We were given a diameter of 0.1, so I can type an equation equals pi divided by 4 times 0.1 times 0.1, hit enter, and then it evaluates that equation as 0.00785. In addition to equations, you can also define symbols and give those symbols values, and then change those values from one central place in the code. I'll set our flow coefficient to 1. We'll make this a perfect compressible orifice. I'll hit OK and save my model. And now we're ready to run. So as it runs, you see scrolling by text telling you that the solution satisfied the convergence criteria in so many iterations and what the time step is. Now, we can open up the output file, which is a text file, and this is fine for steady state models, but in an unsteady model, it's really hard to see what the change in pressure or temperature is by scrolling through a lot of text. So instead, it's easier to open up WinPlot. WinPlot is a code developed at NASA Marshall as well, and it is also available from software.nasa.gov. Sorry about the phone. I should have unhooked that beforehand. So I will open up WinPlot and go to the parameter selection. And we can plot P1, the pressure in node 1. That's the pressure in our tank. So we can see the pressure dropping from 100 psi down to 25 psi in 300 seconds, or 5 minutes. We can plot T1, the temperature in the tank. So the air in the tank goes from 80 degrees Fahrenheit down to minus 110 degrees Fahrenheit, assuming an adiabatic blowdown. We'll talk more about that in a moment. M1 is the mass in the tank. So from 5 pounds down to just under 2 pounds. And F12 is the flow in branch 1-2. So our flow rate drops from 0.018 pounds per second down to about 0.005. And so the flow rate's tapering off as our pressure in the tank drops off. Now, I had mentioned that we are assuming an adiabatic blowdown here, that is, no heat transfer from the wall. Turns out that if you have an ideal gas and no heat transfer, there is a simple equation that can calculate the change in pressure with respect to time. And that's shown here at the bottom of this screen. And so the purple descending line is the analytical solution and that compares well with GFSSP. The three rising lines show the error in GFSSP versus the analytical solution. And so if we use a 1-second time step, we end up with a difference of about 0.1 psi from the analytical solution. As we decrease the time step, that goes down to about 0.03 psi. Now, what would happen if we decided to be more realistic and include heat transfer from the wall? We can do that by going to our Circuit tab and activating Conjugate Heat Transfer. So now there's some more items over here, including the solid node. So I will add a solid node to represent the mass of our tank wall. And I will connect our tank wall to our fluid mass by adding a conductor. We were given a 10 cubic foot tank, so I'll just assume it's a sphere, which means the diameter is 2.68 feet. If we then do the calculations for such a sphere with a wall thickness of 1/2 inch, it works out to be 471 pounds of stainless steel. So for mass, I'll put 471 pounds. For material, I'll select stainless steel 304. We have a library of about 40 common metals built in GFSSP, and you can see what values of CP and K are being used in this library. So here, stainless steel at roughly room temperature, we're looking at about 0.11 BTUs per pound degree Rankine. You also have the ability to add up to 5 user-defined fluids where you supply the CP and K as functions of temperature. Our initial temperature will be 80 degrees Fahrenheit, just like the wall. If we wanted, we could add a heat source to the wall, but I'll just leave that set to 0. Going to our convection conductor, I'll go to properties. It wants to know the wetted surface area, the heat transfer area. So again, assuming a sphere of 2.68 feet diameter, that's 3,250 square inches. And then it wants to know about our heat transfer coefficient. We can set it to user specified and then supply a constant value. But I'm going to do a natural convection correlation, assuming a vertical plate. And so this is just the Nusselt number is some constant times a Rayleigh number to the n power. But to calculate the Rayleigh number, we need to know the characteristic length. So I will make that equal to the 2.68 foot diameter of the tank. Right. So before I rerun, I'm going to go ahead and change the name of this model from demo1.dat to demo1.cht.dat. That way I won't overwrite my earlier results, CHT standing for conjugate heat transfer. And then I will run the model. And I will open WinPlot. And I will also go ahead and drag in our earlier result from the adiabatic blowdown. So if I plot the pressure in the tank now, blue was our earlier result. Red is our new result when we include heat transfer from the wall. So after 5 minutes, the pressure is about 33 psi instead of 25. And that is because the temperature of the fluid is not as cold as before. When we include heat transfer from the wall, we're looking at about a steady temperature of around 45 degrees Fahrenheit, instead of it going all the way down to minus 110. I can plot the temperature of that solid wall. Now this was a very massive tank, so the solid wall only cooled off from 80 down to about 78 degrees. The calculated heat transfer coefficient, H, You can see it's changing over time. It's given in BTUs per second foot squared Fahrenheit. One of the nice things about WinPlot is you can plot equations, so I'll go ahead and multiply by 3600. And so in the more normal BTUs per hour foot squared Fahrenheit, we see we're about 1.5 BTUs per hour foot squared Fahrenheit, which is typical of natural convection. Now, I had mentioned that you can write user subroutines in GFSSP. Let's do a simple one now where we assume there is an electric heater inside the tank and that when the temperature drops below 60 degrees Fahrenheit, the heat turns on, and when it goes above 65, the heat turns off. So I will change the name of the model again to add .heater to it. I will turn on user subroutines and ask for a new user module file. So this will copy our template into your working directory. And then I will hit Edit User Subroutine. And it opens our user subroutine editor. So this is all a Fortran file, but you can see it's almost entirely comments. These are just blank user subroutines. We're going to go to subroutine bound user. This is called at the beginning of each time step. So at the beginning of each time step, we will check the temperature in our node, and if it's below 60, we'll add heat. I will go ahead and define the heater power as half a BTU per second. That's roughly 500 watts. If you've ever used Cinda before, you're familiar with the concept of absolute node numbers and relative node numbers because of the way things are stored in memory. GFSSP is similar. You have to get the pointer to a node in order to find out information about it. But I can right-click, go to indexing, and ask for the index of a node. And I want to know the pointer to node 1. And it will return to me IPN, integer pointer to the node. Now I'll say if the fluid temperature in the node pointed to by IPN is less than 60 Fahrenheit, but I have to convert to Rankine, then the heat source into the node pointed to by IPN is equal to heater power. Otherwise, if the fluid temperature is greater than 65, converted to Rankine, then the heat source into that node will be 0. And what happens if it's in between 60 and 65? Nothing will happen, and it will just take the value it had before. So now I'll go ahead and hit save, and then compile. And it calls my Fortran compiler, compiles this user subroutine, and links it to the main GFSSP source code and creates a new executable. We normally work with Intel Fortran, but you can also use the G95 freeware compiler. It does run a little bit slower than the Intel executable, but it works all right. Now, if I look in my working directory, there is a new executable that was just built that contains my custom Fortran. If I go to the model properties, it no longer says for solver executable, it no longer says GFSSP version 702, it has my new custom executable. So let's run this model, and I will open it in WinPlot. And I will go ahead and add in our previous result that had conjugate heat transfer. If I plot the temperature, initially the two models are the same until we hit the 60-degree mark, and then this new one with the conjugate heat transfer, it starts adding heat until it reaches 65, and then it cycles on and off. And you can see as we have less and less air in the tank to absorb that heat, the cycling occurs more often. So now I will go back to our presentation. Another application of GFSSP is water hammer, fluid transients in general. One type is water hammer. That's what happens when you have liquid flowing in a pipeline and then you close a valve very quickly. You can sometimes get a pressure surge. So for example, in this case, we have a source of liquid oxygen at 500 psi. It flows down a 400-foot pipeline and reaches a valve. Steady state, it's flowing at 0.1 pounds per second, but if we close this valve in 100 milliseconds, 0.1 second, that's not enough time at the lock speed of sound for the information to get back up to the source. And so you can end up with a pressure surge right here at the valve. And it's important to be able to predict these surges to make sure that you don't end up blowing out your pipes. I'll show that example. That is a pre-built example. It's our example 15. And so we discretized that 400-foot pipeline into a series of 5 pipes. There's our upstream boundary at 500 psi and our downstream boundary at 450. And the valve is a restriction to which we turn on the valve open close option. And that's just an option where you can change the area of a component as a function of time by supplying a history file. So if I run this model and open WinPlot, if we plot that pressure, we can see that the pressure goes all the way up to 625 psi, even though the driving pressure at our source was only 500. Because it came crashing to a halt so fast, we ended up even higher than our source pressure. Now, GFSSP can be compared to the method of characteristics, which is often used for water hammer. So in this plot here, we see that example that we just saw. GFSSP's result is shown in purple, and the blue lines show the result from the method of characteristics. They show a pretty good comparison. Another type of fluid transient is that of sudden valve opening or priming. Sometimes in propulsion applications, you may have liquid behind a valve, and on the other side is empty pipe, either gas at low pressure or just completely evacuated. And then you get into space and you open that valve. Often this happens when you're using hypergolic propellants. So the liquid comes rushing into the empty space, hits the dead end, and you get a pressure surge. So one of the experiments we've done in this case was a Georgia Tech experiment where they pressurized a tank of water. It was connected to a pipe, and at region CD, there was a valve. And on the other side of the valve, it was just initially air at atmospheric pressure. They would open that valve, and water would come rushing in and hit the dead end. And the valve opened in about 0.2 seconds of time. So when we model this in GFSSP, here we have the test data shown in as the black dots, and then the different lines, the dashed lines, the solid lines, show the GFSSP's results, assuming running with different time steps. So you can see the time step does have a slight effect on the result, but the prediction of peak pressure is pretty accurate. The driving pressure here was 100 psi, but our peak pressure was 250 psi. Sometimes in propulsion applications, especially when working with cryofluids, we're interested in chill down of transfer lines. And this can be on the ground, long lines going to propellant tanks on a vehicle, or it can be shorter lines going between a spacecraft tank to an engine, or going from an on-orbit depot to a spacecraft tank.
Question, Andre.
Yes.
They would like to know in the previous example why you discretized the pipe into several segments instead of doing one continuous run.
Um, that is to capture the So yeah, in water hammer type analysis, you're trying to capture the change in density with respect to pressure. And if we had only done one pipe, it would have been all the same um, density throughout the pipe. So to capture that change in the pipe, we discretized it into 5 segments. And in fact, that particular model was also run with like 10 pipes as well to see the effect of discretization. But going from 5 to 10, there wasn't a big effect. But say going from 5 down to 2, that does affect your answer. So we have modeled the transfer line chill down experiment from the 1960s done by the National Bureau of Standards. They had a 200-foot long section of pipe that was vacuum jacketed, and they had a dewar, 300-liter dewar filled with either liquid hydrogen or liquid nitrogen. They tested with both, and they would open a valve and let it flow through the pipe, and they recorded how long it took the pipe to chill down, taking measurements at 4 stations. So that is also an example that we include with the installation. That's our example 14. So in GFSSP, that experiment looks like 30 pipes connected to 30 solid nodes. And here we're discretizing because we want to capture the effect of the change in properties as temperature is changing along the flow path. And if we plot the solid temperatures at 4 different locations, we see that close to the inlet, the temperature drops very rapidly, whereas the further you go downstream, you get kind of a slow initial chill down from the vapor, the cold vapor that's flowing by, to a faster chill down once you start getting hit with the liquid vapor mixture, the two-phase liquid vapor mixture. And it chills down in about 55 seconds, which agrees pretty well with the test data. The last thing I'll cover today, the last use of GFSSP in propulsion applications I'll cover today is tank pressurization. Um, GFSSP has a built-in pressurization option, which allows you to do a simple system-level pressurization model where your ullage node, your tank is discretized into an ullage and a propellant node, each representing one node. And so as the tank is pressurized and draining, you have your ullage volume increasing. So you need more and more pressure coming in. And you have your propellant node decreasing because it's draining to the engine. As this happens, the amount of hydrostatic head, rho GH, of the propellant is going to decrease. So GFSSP keeps track of the change in the height of the propellant because you've given it properties of the tank volume properties as a function of height. And there's heat transfer going on between your pressure and gas, which is usually helium, but not always. And so there's heat transfer going in from the warm helium coming in and your cold cryogenic propellant. So that causes the pressure to lose pressure. So then you need to add even more. You also have heat transfer going on between the pressurant and the wall. That also tends to cause you to lose pressure and require even more helium be added. There's some heat conduction going on between the uncovered portion of the tank and the tank that's still exposed to the cryopropellant. And Optionally, you can add a user subroutine if you want to try to model mass transfer between the pressure and propellant. A crude way to do that is to take your value of heat transfer into the propellant, divide by the heat of vaporization, and make that a mass source into your ullage node. But there are fancier ways to do that as well. So the purpose of a tank pressurization analysis is to give you an idea how much pressure and gas you're going to need to keep your tank pressurized and whether you can keep it pressurized to keep your propellant in the run box. So what is the pressure of the propellant going to be when it reaches the engine run box, reaches the engine inlet? A large example of this is our model of the helium pressurization system down at Stennis, where they did testing of the fast track engine. I'll show that. That's another example that we include with GFSSP. That's our example 12. So we have helium coming in at 750 psi from ground system. Some of it goes down the left path to the engine. Some of it goes down the center path to the LOX tank, where the LOX ullage is node 54, the LOX propellant is node 56, and they're separated by what we call a pseudo-boundary node to represent the surface of the propellant. There's a control valve here that will bang open and closed in order to maintain the pressure in the LOX ullage. Then coming over to the far right, we have the same thing except going to the RP1 tank, which is at room temperature, so there'll be less heat transfer going on. So if I were to plot this, so here is the pressure in the LOX tank ullage. So the control valve was set to keep pressure between 56 and 60 psi early in the run, but then later on for the start box, but then later on for the run box, it was told to keep it about 53 psi. You can see the control valve cycling on and off and the pressure rising and falling. Here's an example of some of our of it when you run this model and compare it to test data. In this case, at T minus 420 seconds, the LOX tank was pre-pressurized. And so it rises up in pressure, and then because of the cold temperature of the wall, the temperature of the cold LOX, pressure drops. You have to add more helium, and it cycles like this. And then at T equals 0, the engine actually starts. So now you have very rapid cycling because the tank is draining and your ullage volume just keeps growing and growing. And you can see GFSSP provides a pretty good approximation of the actual test data. It does get a little iffy here near the end of pre-press. When it comes to these tank pressurization models, the most uncertain part of the model is going to be your heat transfer coefficient between your ullage gas and your wall and your ullage and propellant. So that brings me to the end of my presentation. Again, for more information, check out our website, nasa.gov/GFSSP. Also, you can Google GFSSP, and this website is the first thing that you'll hit. Or you can contact Alec or myself directly at our email addresses. And I just want to thank you again for coming and listening to me. And I'm open for any questions.
Okay, not seeing any questions just yet in the chat, but we've got about 10 minutes till the start of the next presentation. So if one comes to you in the meantime, please do put it in the chat and we'll field it to our presenter. We've got one from Dimitri. Is it possible for the model to have rotating and stationary parts within a network? If so, How is that modeled by transfer from absolute or relative motion or vice versa?
Um, so we do have for turbopump modeling various branches that model pressure drop in rotating parts. Um, and there is also the possibility of, I assume what he's getting at here is the volumes of your nodes can change. Normally, nodes are constant volume. And that can be done as well. We have an example of a couple examples of that, like a piston in a cylinder and um, one with a rotating bearing. Um, so yes, you can do that. It will probably require some user subroutine work. But yes, it can be done.
Okay, on a somewhat related question. So let's say I wanted to model a fluid system that has a node that might, like in a ramjet, you'd have a shock train that would provide some compression, and you'd have a model of what the inlet and outlet conditions are. But that could change in length or shift within the system. Is it possible to make segment lengths adjust in time?
Yes, it is possible to do that. You would have to write a user subroutine though, and change the properties of the segments with time. The mention of ramjet, it does. I do need to point out that GFSSP is a subsonic code. So anything supersonic is doubtful.
Okay, so just maybe the back end of the ramjet where it's
Yeah.
gone sub. How close to transonic can GFSSP handle?
That I'm not too certain of. We've only done a limited number of models where we've compared solutions. Our example 3 shows flow in a converging diverging nozzle, and it agrees pretty well, gets the flow rate pretty well, and it predicts at what point the flow is going to choke, at what pressure ratio, upstream over downstream, what ratio it's going to choke. But we haven't really done any detailed comparisons of high-speed flows.